real-time language translation. So if someone's talking to you in another language, you'll have real-time subtitles on the world. And search engines won't wait to be asked a question. They'll actually be listening in on your conversation. If they see you getting stuck with something or it thinks there's some information that would be of value to, it'll just pop up information like it were a friend trying to help you out. As we get to 2029, these technologies will be millions of times more powerful than they are today, and they're already deeply influential. We will have completed the reverse engineering of the human brain. We will have very intelligent machines, and they will be making us smarter and extending our reach, and they will actually keep us healthy from inside. These blood cell-sized devices in our bloodstream, which will have very powerful computers in them, will go into our brains through the capillaries and interact with our biological neurons. They'll create full immersion virtual reality from within the nervous system. So, for example, if I want to go into a virtual reality environment, the nanobots will shut down the signals coming from our real senses, my real eyes and ears and so on, create a virtual reality environment, and to my brain it will feel like I'm in that environment, incorporating all 5 senses. And so as I move my hand, it'll actually move my virtual hand. I'll have a body in these virtual reality environments. It doesn't have to be the same body as I have in real reality. And we'll be able to vastly expand our educational and communication capabilities. Most importantly, it will be an expansion of human intelligence. And that's what our technology does today. The fact that I can take a device out of my pocket and expand my intelligence today is already an extension of who I am. And that's really what's unique about the human species. We didn't stay on the ground, we didn't stay on the planet, and we have not stayed with the limits of our biology. And I'll leave you with this last trend. This has been from health and biology, not as an information technology, just hit or miss, but we've made a lot of progress. It was not in the interest of the human species for people to live that long 1,000 years ago because there wasn't that much food. So once you got done raising your kids, you're just using up the precious food and resources of the tribe. And so human life expectancy was in the 20s 1,000 years ago. It was 37 in 1800. There was no sanitation. People got a lot of bacterial infections. There was no antibiotics. And the human life expectancy was 37. It's now pushing 80. But now that health and medicine is an information technology, it's going to double in power every year. These technologies will be 1 million times more powerful in 20 years. And according to my models, 15 years from now, we'll be adding more than a year every year, not just to infant life expectancy, but to your remaining life expectancy. So as you go forward a year, your life expectancy will move on away from you. So if we can hang in there for another 15 years, we may get to experience the remarkable century ahead. Thank you very much.
Proceed with the questions and answers. The qualia can be modeled mathematically or they have to be generated by harnessing the laws of physics. Do you want me to continue or?
Well, let me deal with that. Those are some good questions. And we're in an early stage of trying to understand the human brain. We're getting a lot of data, and it can be very tricky to try to figure out how it works. We're realizing that a lot of properties of the brain are what are called emergent properties. They're not based on very specific logical tasks, but the overall statistical effect of many different things going on at the same time. My own field has been an effort called pattern recognition, trying to recognize patterns, and we're realizing that that's actually how the brain is built. We don't understand language, for example, by understanding logical rules, but rather by seeing patterns. That's the power of human intelligence. And it's an emergent property where lots of things happen at the same time, and certain patterns emerge in the brain representing our judgment on either recognizing a situation or making a decision. And there's a whole area of mathematics on emergent systems, self-organizing systems, that attempt to model this type of process, and it seems to be the best type of mathematics to use. But we have to actually go through many different attempts to model and simulate these processes. Many of them don't work out, but finally we come up with a model and simulation that has very similar properties to the human brain region that we're trying to model. And this is an exponential process. We're getting more and more data. We can actually see now inside the brain at a very precise level. We can actually see our brain create our thoughts. We can see our thoughts create our brain, but that's part of the process. As we think about things, we're actually creating new connections. And our brain is actually made up of all the thoughts that we've thought for the last number of years. And the best way to actually keep your brain active is, in fact, to keep it continually challenged, because our brain is not fixed. It's constantly reorganizing itself. But this is actually the most challenging area in science right now. But ultimately will give us a key to the most powerful and important process in the world, which is our own intelligence. And if we can understand it, we'll have more insight into ourselves, and we'll also be able to use that insight to actually make ourselves smarter.
The next question is, why do you mention in the IEEE Spectrum magazine that the brain is a probabilistic fractal? Is it related to the cortex isomorphism? Why don't you write a book about all the mathematical tools needed to program a strong artificial intelligence? Many singularitarians like me will enjoy it. That book will accelerate the emergence of the singularity.
Well, it's interesting. I'm actually, a book that's coming out next year is about health, but after that, my next book will be about exactly that. Will be about how to model the brain and what we know about the brain, and also how we can build new brains, and then how we can merge with those brains to make ourselves smarter. In terms of the probabilistic fractal, this brings up an issue about how complicated is the human brain. And if you look at the human brain, it looks very complex. But there's also an image called the Mandelbrot set that also looks very complicated. But it's actually, it is a fractal. It's a very simple rule that's repeated over and over again and creates a very complex image. And the brain is itself a fractal. It has a number of rules that are repeated over and over again and create a very complex structure, but it's not as complicated as it looks. Take the cerebellum, which, as I mentioned, we have simulated, and that's where we do our skill formation, like catching a fly ball is done by the cerebellum. And if I showed you the cerebellum, and there are images of them from actual brain scans, it looks immensely complex. And if I said, here, figure this out, figure out how this works, reverse engineer it, you go, well, this is infinitely complicated. This will take centuries to figure out. But actually, it's not that complicated, and we have figured it out. There's only a few genes that control the wiring of the cerebellum. Basically, the genome says the following about the cerebellum. It says, create one module with these 4 different types of neurons, organize it like this. Now repeat that 10 billion times and add some random variation with each repetition. And so with that constant iterative process, basically a fractal process, the cerebellum is wired and it looks immensely complicated. But it's actually through the repetitive application of a few rules. And the rules are not simple, but they're not that complicated. There's actually a billion-fold difference in how complicated the brain looks versus the amount of complexity in the design of the brain. So that's why I say the brain is a fractal. It's a probabilistic fractal because there's a certain amount of randomness in how it's wired. And then the brain interacts with our environment and reorganizes itself to reflect its own judgments about what it's experiencing, and that's part of the process. But it is a probabilistic fractal, so it's not. There's only about 50 million bytes of complexity of information in the genome. The amount of information in a mature brain is 1 billion times greater than that, but the design is a level of complexity that we can manage.
Okay.